In last lecture, we have seen the proof of the Morse theorem is first. In this lecture, we will continue to the proof of the Morse theorem. Okay. Case 2. Let n be a negative integers, that is n equal to -10. Here n is positive. Then LHS of statement the Morse theorem. Cos theta plus I sin theta bracket. Yeah. Now n, put the value of n equal to m. So equal to the cos theta plus I sin theta raised to m. Now we use the third rule, means data transfer name. Okay, is equal to the power is minus m. So we convert this power into positive term. Now is equal to the 1 divided by cos theta plus I sin theta raised to m. Okay. So we know in case first the positive integer, the theorem of the Morse theorem is valid, and therefore we put we use the theorem of the Morse theorem by case first. So we can write the statement this value is equal to the 1 divided by cos m theta plus I sin m theta. Okay. Now this is a complex number. Now we simplify this complex number by using the rationalization process. Rationalization process means change the sign here and multiply numerator and denominator. So is equal to the 1 divided by cos m theta plus I sin m theta. Now we change the sign and multiply numerator and denominator. Cos of m theta minus I sin m theta divided by cos of m theta minus I sin m theta. Now, okay, is equal to the cos of m theta minus I sin of m theta divided by here, which is a plus b and a minus b. Now its multiplication is a square minus b square. So like that. So cos of m theta is a and sin of m theta, I into sin of m theta is b. So cos square m theta minus I square sin square m theta. Now we know that the value of I square is equal to -1. So we put the values. So the simplification is cos of m theta minus I sin of m theta and divided by cos square m theta minus plus sin square m theta. So this is identity of trigonometric formula. Since cos square m theta plus plus sin square m theta is equal to 1. So we use the trigonometric formula. Okay, here the value here put, and therefore we get the result is equal to the cos of m theta minus I sin of m theta. Now again we use the trigonometric formula. Here the cos of minus theta is equal to the cos theta. So here cos of m theta is equal to the cos of minus m theta. So we put value here, and also here minus sin of m theta is equal to the sin of minus m theta. So we put value plus I sin of minus m theta. Okay. So this is the trigonometric formula that we use. Okay. Now this is equal to the, so minus m, it is a n value. So we start from n is a negative. So we put the value minus m is equal to n. So cos n theta plus I sin n theta. Okay. Now we start from the statement of the Morse theorem. From LHS, we get the result of RHS. And hence this shows that the theorem of the Morse theorem is valid for all negative integers. Okay. It is case 2. Now case 3. Let n be a proper fraction. Say n equal to p by q. Okay. Where p and q are integers. Now, without loss of generality, we can select to be a positive integer. Then, by case first, we know that for the positive integers, the theorem is valid, and therefore, cos of theta by 2 plus I sin theta by 2 raised to q is positive, and therefore theorem is valid and is equal to the cos of q into theta by q plus I sine q into theta by q. Now q answer, and hence one of the values of cos theta plus I sine theta raised to 1 by q is cos of theta by q plus I sine theta by q. It is positive. So this is positive value. So theorem is valid for this. Okay. That is one of the values cos theta plus I sine theta raised to p by q. Again p is positive. Is therefore we can write this. So cos theta by q plus I sine theta by q. Now first 1 by 2 we can write this and then raised to power p, and that is one of the values of cos theta plus I sine theta raised to p by q is, again we use this for positive integer theorem is valid, and therefore is cos p divided by q into theta plus I sine p divided by q into theta by case first and case second, and hence one of the values of cos theta plus I sine theta raised to n is cos of n theta. So p by q is n. So cos of n theta plus I sine of n theta, where n equals p by q. This shows that the uh, for theorem is valid for n equal to fraction value. So this is the case 3. Hence the proof of De Mor's theorem. Now next question. Question 2. Okay. Question 2. Prove that for all rational numbers, comma, one of the values of cos theta minus I sine theta bracket raised to n is cos of n theta. So we are using here. So cos of n theta minus I sine of n theta. Now here we have seen in De Mor's theorem the De Mor's theorem statement. De Mor's theorem is proof. Okay, statement is cos theta plus I sine theta raised to n is cos of n theta plus I sine of n theta. Here question 2, we prove the result for the negative value. So cos theta minus I sine theta raised to n is cos of n theta minus I sine of n theta. So this is question 2. Okay, now its answer is, now we use the De Mor's theorem. We know that De Mor's theorem for all rational number, one of the values is equal to this. This is the De Mor's theorem. Cos theta plus I sine theta raised to n is equal to the cos of n theta plus I sine of n theta. Now equation 1. Now also we know that trigonometric formula. Okay, this is cos of minus theta is equal to cos theta and sine of minus theta is equal to minus sine theta. Now equation 2. Okay, now we start from the LHS of this. So therefore cos theta minus I sine theta raised to n, okay, is equal to the, we using this trigonometric formula here. So we put cos theta, so value is equal to the cos of minus theta here. So bracket cos of minus theta. Now plus minus sine theta, we put this value for this. Okay, so plus minus sine theta is equal to this. So plus I sine of minus theta in bracket raised to n by equation 2. Okay. Now we know that for the positive integer n, so by using the De Mor's theorem, equation 1. Now yeah, so is equal to the cos of minus m n multiplied the cos of minus n theta plus I sine of minus n theta by equation 1. We use this, and therefore again we use the trigonometric formula here. Cos of minus theta is equal to cos theta, reverse value cos of minus n theta is equal to the cos n theta. And again cos sine of minus theta is equal to the plus I sine of minus n theta is equal to minus I sine of n theta. Now by equation 2, we use this. And hence, for all rational number n, one of the values, so we get the result of IHS. Now we start from LHS, we get the result. Okay, right. And hence, for all rational number n, one of the values cos theta minus I sine theta raised to n is cos of n theta minus sine of n theta. Hence the answer of this question. Okay, now examples on De Mor's theorem. Okay, here we use the statement of a De Mor's theorem and we solve the examples here. Okay, first example, example 1. Simplify. Okay, simplify this. Now bracket cos of 2 theta minus I sine of 2 theta raised to 5 into next bracket cos of 3 theta plus I sine of 3 theta raised to minus 4 divided by cos of 3 theta plus I sine of 3 theta bracket is to minus 2 into next bracket cos of 5 theta minus I sine of 5 theta bracket is to 3. Now we simplify this result by using the De Morgan theorem. Now solution. Okay. We know that by statement of a De Morgan theorem is okay cos theta plus I sine theta bracket is Pn is equal to the cos of n theta plus I sine of n theta. So this is the most important statement of De Morgan theorem. We use this statement for simplifying this result. Okay. Also, we know that the trigonometric formula, okay, cos of minus theta is equal to theta and sine of minus theta is equal to minus sine theta. So these two formulas we use for simplifying this. Okay. Now we start each factor simplification. So first factor is bracket cos 2 theta minus I sine 2 theta raised to 5 is equal to the. Now we use trigonometric formula here first. Okay. Cos theta for this. So here. So bracket cos of minus 2 theta plus minus sine theta for this. Okay, we put here plus I sine of minus 2 theta raised to 5. Here, okay. Now uh, we use the De Morgan theorem statement here. So we start from this, we get this. So here we put 5 multiplied here, n is here. So uh, reverse the statement here. So minus 2 in the in the power 5 into minus 2 here. So in bracket cos theta plus I sin theta raised to 5 into minus 2 is minus 10 by 1 De Morgan theorem. Okay, we use this statement. Okay, now uh, we simplify each factor in the form of a base same base step. Okay. Now next factor we consider cos of 3 theta plus I sin of 3 theta raised to minus 4. Again we use the De Morgan theorem statement. So reverse part we use here. So this is reverse part. So in bracket we use it is equal to the cos theta plus I sin theta and power 3 is multiplied to the power minus 4. So minus 4 into 3. So minus 12. Okay. Now this is simplification. Again like that. Okay, by using the this De Morgan theorem. Okay, next bracket factor cos of 3 theta plus I sin of 3 theta raised to minus 2. Again simplifying we using this. Okay, cos theta plus I sin theta raised to power minus 2 multiplied by power 3, so minus 6. Now next factor cos of 5 theta minus I sin of 5 theta bracket raised to 3. Now again we use the trigonometric formula here. Okay, so cos of theta for this value we put here. So cos of minus 5 theta plus minus 5 theta is equal to the plus I sine of minus 5 theta raised to 3. And again we use the statement of the De Morgan theorem reverse for this. Okay, and therefore this shows that cos theta plus I sin theta raised to power 3 into minus 5, so minus 50. So by using the equation 1 of De Morgan theorem. Okay, now this simplification factor is in one base, same base steps. So we use this simplification in this example. So here, hence the given expression can be written as now LHS. Now this is given example is equal to the each factor simplification we put here. Okay. So cos of 2 theta minus I sin of theta raised to 5, its simplification is this cos theta plus I sin theta raised to minus 10. We put here. Okay. Now next factor simplification is cos theta plus I sin theta raised to minus 12. We put here. Now next, okay. Third is here put and fourth factor is also here. Okay. Now here we have seen that each factor simplified in one base. Okay, cos theta plus I sin theta is uh, same value here. cos theta plus I sin theta is also same here, cos theta plus I sin theta, cos theta plus I sin theta from same values. So we use the formula for Surde's rule. Surde's rule means gapatan formula. So now base same, so gapatan the power the addition of it. Okay. Now this cos theta plus I sin theta raised to minus 10 minus 12. Okay. And in the denominator factor, when we take numerator, now power, sign of power change will be changed. Okay. Now cos theta plus I sin theta raised to 6 in the numerator and cos theta plus I sin theta raised to 15 in the numerator. So it's also power base is same and therefore addition is like that. Cos theta plus I sin theta raised to power minus 10 minus 12 and plus 6 plus 15. So this is subtraction, this is the calculation, we get value minus 1. Okay, so cos theta plus I sin theta raised to minus 1. Now, again we use De Mor's theorem here. Okay, so minus 1 is multiplied here and therefore we get the result cos of minus theta plus I sin of minus theta by De Mor's theorem. And again we use the trigonometric formula. Cos of minus theta is cos theta, sin of minus theta is minus sin theta by equation 2 to get the result. And therefore, the our this value is equal to this is the simplified value of the given example. Okay, hence the solution of given example 1. Now, example 2. Prove that bracket root 3 plus I bracket is to n plus next root 3 minus I raised to n is equal to the 2 raised to n plus 1 into cos of n pi by 6 where n is a positive integer. Okay. Here we start from LHS. Okay. Now solution. Now here we know that polar form, this is a complex number. This is a complex number. So we simplify first by using the polar form of a complex number we have seen in first lecture. Okay, we know that polar form of a complex number, like x plus I is equal to the r into bracket cos theta plus I sin theta. Okay, this is the polar form of complex number. Now equation 1, where r value is equal to root x square plus y square and theta equal to tan inverse y by 6. Now this is the expression second. Okay. Now each of complex number we simplify first and then we take the addition. Okay. Now let first complex number, let x plus I is equal to root 3 plus I. Okay. Therefore, we have now compare these two complex number, we get the value x equal to root 3. Now real part both sides are equal and then imaginary part both sides are equal. So x equal to root 3 and y equal to 1 and therefore x equal to root 3 and y equal to 1. Okay. Now we find from equation 2 we find r. So r equal to root x square plus y square, put k value. So root 3 square plus 1 square. So is equal to the root 3 plus 1 is equal to root 4 is equal to 2. So the value of r is equal to 2. Now theta equal to tan inverse y by x. Now we put value y is equal to the tan inverse 1 upon root 3. Now we know that the trigonometric formula, okay, the triangle 30, 60 and 90-degree triangle. Okay, the side of this triangle is 1 from the angle 30 degrees and diagonal is 2 and the next side is root 3 and therefore this value is angle is pi by 6. 1 upon root 3 means uh, uh, by using this triangle the ratio of the front side, length of front side and diagonal side. Okay, so this is a, so 1 upon root 3 is tan inverse of 1 upon root 3 is a pi by 6. Okay, so theta equal to the angle pi by 6. Okay, by using the triangle rule. Okay, now next, therefore from 1 root 3 plus r. Okay, we put the value, we calculate polar form of this r value to cos So theta value pi by 6 plus I sine pi by 6. Okay. So this is the polar form of the given complex number. Okay. This is now taking the n power to the both sides by using the De Morgan's theorem. Okay. Now we take n power so to the both sides. Root 3 plus I raised to n is equal to the 2 raised to n into bracket raised to n. And here we use the De Morgan's theorem. And therefore 2 raised to n bracket cos pi by 6 plus I sine pi by 6 raised to n. Now we use the here De Morgan's theorem and therefore is equal to 2 raised to n cos of n pi by 6 plus I sine of n pi by 6. Now equation 6. Now we simplify this. We get the complex number form. Now similarly, we take another complex number. Okay, here, here. Now we simplify this value of the again complex number here. Okay, like that. Similarly, we can find this value. Okay, and therefore similarly, root 3 minus I raised to n. Okay, is equal to the here plus value. Now here plus. Now here minus value. So it is also minus. Now then similar value is equal to 2 raised to n into bracket cos of n pi by 6 minus I sine n pi by 6. Okay, by using the De Morgan's theorem and the about similar process we use here. Okay, so we get this result. Okay, now this is equation 4. Now adding these two, LHS factor is adding these two. Okay, adding equation 3 and 4, we get now first root LHS root 3 plus I raised to n plus bracket root 3 minus R raised to n. Now this is LHS. Now is equal to the value is here in RHS 2 raised to n 2 raised to n into bracket cos of n pi by 6 plus I sine n pi by 6. So this is the value of this and plus next value from equation 4 2 raised to n into bracket cos n pi by 6 minus I sine n pi by 6. Now 2 raised to n power is common. Now 2 raised to n common in bracket cos of n pi by 6 plus I sine n pi by 6. Now next bracket plus cos n pi by 6 and minus I sine n pi by 6. So this is in bracket. Here we have seen that the plus I sine n pi by 6 is plus and minus I sine n pi by 6. So this these two terms are cancelled to each other. Okay. Now here cos n pi by 6 1 and in same cos n pi by 6 plus. So its addition is 2 into cos n pi by 6 and next 2 raised to n. So 2 raised to n into 2 cos n pi by 6. Now base is same. Now raised to power is n plus 1. Here 1 power and n. So 2 raised to n plus 1 by using the third rule. And therefore bracket root 3 plus I raised to n plus root 3 minus I raised to n is equal to the 2 raised to n plus 1 into cos of n pi by 6. Hence the result. This is the solution of example 2. Now, the remaining part will be continued to the next lecture. Okay, thank you.